Week 3, we will be discussing Chapter 4 this week and taking a look at the X-ray circuit inside and out. So this week we will be looking at the nature of electricity, electrical devices, and the basics of the X-ray circuit and principles of operation. Many types of X-ray equipment are automated, but the RT is not someone who merely just pushes buttons. We have an understanding of the principles of X-ray production and have mastered the art of producing quality images with minimal radiation exposure to your patient. We understand the basic elements of the X-ray machine and the steps that are in the process. Think about a pilot who flies a jet. A pilot that is untrained for that aircraft may be able to get it off the ground and flying, but without some understanding of the actual jet's instrumentation, they're not likely to stay in the air very long, are they? The safety of the passengers aboard that aircraft are going to rest with the training and the knowledge of that pilot. So it's a little similar to us as radiographers. We are responsible for the safety of the patient. The radiation dose that the patient receives depends on our understanding of safe operation of the X-ray machine. And then, of course, the technical factors that we put onto the control panel will result in either a poor image or a diagnostic quality image, which we're aiming for the latter. We want the diagnostic quality image. So the concepts that you're going to learn in this chapter are important to you because they ground your practice in the fundamental understanding of what is happening each time you operate the X-ray machine. So by understanding what is happening with the X-ray machine with each selection that you make at the operating console, you'll be able to use the machine with maximum efficiency and minimal radiation exposure to the patient. You'll also be able to make adjustments in the exposure technique with variations in different machines that you're using and daily operation. You can see here in this picture, this is a machine control panel. This is just one of the several different varieties of control panels that you will see at clinicals or when you're working out in the field. They are all different. Electrostatics is the study of stationary electric charges, and electrodynamics is the study of electric charges in motion. Static means stationary, and dynamic means moving or motion. The electrodynamics is what we consider as electricity. Electric charge is a property of matter, and the smallest units of charge exist with the electron and the proton. Electrons have 1 unit of negative charge, and the protons have 1 unit of positive charge. Electrical charges are measured in the SI system, and the unit is coulomb. 1 coulomb is equal to the electrical charge of 6.25 times 10 to the 18 electrons. A measure of electrons is used because electricity most often results from their movement, except when we're talking about decaying radioactive elements. Protons are generally fixed in their position inside the nucleus of the atom. Electrons are relatively free to move about depending on the material, and some materials such as copper and gold have a very large number of free electrons, making them good conductors of electricity. Glass and plastic have very few free electrons, making them good insulators, but not conductors. There are 5 general principles of electrostatics, and they are the following. Like charges repel and unlike charges attract. The electrostatic force between 2 charges is directly proportional to the product of their quantities, and inversely proportional to the square of the distance between them. This is also known as Coulomb's law. Electric charges reside only on the external surface of conductors, and the concentration of charges on a curved surface of a conductor is greatest where the curvature is greatest. And then the last one, only negative charges or electrons are free to move in solid conductors. In electrostatics, electrification of objects occurs when they gain either a net positive or a net negative charge. An object may be electrified in three ways: by friction, by contact, or by induction. And if you've heard of the experiment involving rubbing a rubber rod with fur, that is an example of electrification by friction, because you're rubbing the two together. Once it's charged, the rod can be discharged by placing it in contact with a conductor. And this is an example of electrification by contact. Electrification by induction is the process by which an uncharged metal object experiences a shift of electrons when brought into the electrical field of a charged object. So induction will occur as a result of the interaction of the electric fields around two objects that are not in contact with each other. This is very useful in the design of the X-ray tube that we will be talking about in Chapter 5. Electrodynamics describes electrical charges in motion, and this motion is associated with electricity. For electric current to move, an electrical potential must exist. Electric potential is the ability to do work because of a separation of charges. If one has an abundance of electrons at one end of a wire and an abundance of positive charges at the other end, that is a separation of charges, and the electrons will flow from abundance to deficiency. Electric potential, current, and resistance are all expressions of different phenomena surrounding electricity. Electrical potential is the ability to do work due to a separation of charges, and the unit of measurement is volt. Current is an expression of the flow of electrons in a conductor, and the unit of measurement is ampere. And then resistance is that property of an element in a circuit that resists or impedes the flow of electricity, and the unit of measurement is the ohm. When viewed at its most basic level, X-ray production is achieved through the manipulation of electricity. The units of measure for electric potential are the volt and current, the ampere. They are the factors that are selected on the operating console of the X-ray machine to produce X-rays. They are expressed in thousands and thousands. And these are electrical terms and are not exclusive to radiology, but are used throughout electricity in general. Electric potential is measured in volts, and it's named for the Italian physicist Volta. And that physicist Volta invented the battery. A volt may be defined as the potential difference that will maintain a current of 1 ampere in a circuit with a resistance of 1 ohm. It is the expression of the difference in electric potential between those 2 points. The volt is also equal to the amount of work in joules that can be done per unit of charge. A volt is the ratio of joules to coulombs, which is volt equals joules divided by coulombs. For example, a battery that uses 6 joules of energy to move 1 coulomb of charge, that's a 6-volt battery. So you've heard of that before, a 6-volt, a 12-volt, and so on. So the exposure factors that are selected on the control panel One of them is the kVp, and that is the kilovoltage peak. Current is measured in amperes, named for André Marie Ampère, a French physicist who made a significant contribution to the study of electrodynamics. The ampere is defined as 1 coulomb flowing by a given point in 1 second. Reflecting the relationship to the definition of volt, it may also be defined as the amount of current flowing with an electric potential of 1 volt in a circuit with a resistance of 1 ohm. For an electric current to flow, there must be a potential difference between the two electrodes and a suitable medium through which it can travel. When we're talking about potential difference, electrons flow from abundance to deficiency and will continue to do so as long as that difference exists, the potential difference. Electricity behaves differently depending on the medium through which it travels. The suitable medium are conductors, and those resisting electric current flow are insulators. But both type of media are important to the production of X-rays. We have to have both of them. Two in particular, there are vacuums and metal conductors, and those are particularly useful in X-ray production. In a vacuum tube, electrons tend to jump the gap between oppositely charged electrodes. This is part of the environment that exists inside of an X-ray tube. We have metallic conductors, and then electrons from the conductor's atoms that will move out of the valence shell to a higher energy level just beyond, and they're called the conduction band. And they are free to drift along the external surface of the conductor. Copper is particularly useful as a conductor and is commonly used as such in electronic devices. Other metals with this characteristic are used extensively in X-ray machines and also in the X-ray tube design. The two types of current, direct current, which is DC, and alternating current, which is AC, are both important to X-ray production and should be understood by the RT. DC is a type of current that flows in only one direction, hence the name direct. And a battery is a good example of that. It has a positive and negative electrode, and when placed in an electric circuit, electrons flow from the negative terminal to the positive terminal. So the current flows in the opposite direction. AC is current that changes direction in cycles as the electrical potential of the source changes. AC is called alternating current, so it's constantly alternating. In the United States, the electricity that flows into homes alternates at 60 cycles per second, and this is expressed as a frequency of 60 hertz. Both AC and DC are used in the basic X-ray production. Resistance is measured in ohms. This is named for the physicist George Simon Ohm, who discovered the inverse relationship between current and resistance. The ohm is defined as the electrical resistance equal to the resistance between 2 points along a conductor that produces a current of 1 ampere when a potential difference of 1 volt is applied. Ohm's law states that the potential difference, which is the voltage, across the total circuit or any part of that circuit is equal to the current, which is the amperes, multiplied by the resistance. So the formula is expressed by voltage equals current divided by resistance. V equals IR. I is current and R is resistance. And of course V is voltage. Resistance is the property of a circuit element that impedes the flow of electricity. The amount of resistance of a particular conductor depends on four things: material, length, cross-sectional area, and temperature. For the material, some materials allow a free flow of current because they have an abundance of free electrons, whereas other materials have resistance because they have virtually no free electrons. With length, the resistance is directly proportional to the length of the conductor. A long conductor has more resistance than a short one. For the cross-sectional area, a conductor with a large cross-sectional area has a lower resistance than one with a small cross-sectional area because there is greater external surface area on which electrons can travel. Temperature: with metallic conductors, the resistance becomes greater as the temperature of the conductor rises. Although resistance may sound like a hindrance to the X-ray production process, actually it's useful and it's an important part of the process of X-ray production. So we have to have that resistance to be able to produce the X-ray photons. Conduction and insulation. These are properties of elements and materials that we use every day. Conductors are those materials with an abundance of free electrons that allow a relatively free flow of electricity. Copper typically is a conductive material. Its valence electrons are relatively free and will readily move to the conduction band. This will allow a free flow of electricity. Gold is also a good conductor, but it's considerably more expensive because it's considered a precious metal, so it's not widely used because of this purpose. Water is also a good conductor of electricity because of the mineral impurities it often contains. Most non-metallic elements are made up of atoms with tightly bound electrons and do not conduct electricity well, even when attracted by a potential difference. These materials are insulators instead of conductors. Insulators have virtually no free electrons, are very poor conductors of electricity. But it is this property that makes them particularly useful in containing the flow of electricity. So covering a copper wire with rubber or plastic will insulate the wire and restrict the flow of electricity to the copper wire. This is the case with an electric cord or an extension cord. Glass, ceramic, and wood are also good insulators. And this combination of conductors and insulators is prevalent in our daily life. We use, combinations of this everywhere, in our house, in our car, obviously in the X-ray machine, but pretty much everything that has electricity running through it. In between these extremes are called semiconductors. And these are materials that will conduct electricity, but not as well as the conductors. And they will insulate, but not as well as the insulators. These semiconductors are silicon, germanium, and diamond. And the semiconductor properties are very useful and are also very widely used in electronics. An electric circuit is a closed pathway composed of wires and circuit elements through which electricity may flow. This pathway for the electricity must be closed or complete for the electricity to flow through. This is what is meant by a closed circuit. An open circuit is one in which the pathway is broken, such as when a switch is turned off. So turning off a switch opens the pathway, and turning on a switch closes the pathway. The elements of a circuit may be arranged in series. It's called a series circuit. or also in parallel called a parallel circuit. And if there's a combination of both series and parallel, it's called a series parallel or a combination. A series circuit is one which the circuit elements are wired along a single conductor. And a parallel circuit is when it is the circuit elements a bridge or a branch across the conductor, and the calculation of voltage, current, and the resistance differ between the two, and the rules for each are summarized on the next two slides that we'll talk about. We're going to talk about the rules for the series and the parallel. An X-ray circuit is a complex version that has different voltages and currents flowing through different sections. In a series circuit, the total voltage is determined by multiplying the total current by the total resistance, or by summing the individual voltage values. The total resistance is found by summing the values of the individual resistance, and the current in a series circuit is equal throughout the entire circuit. Total voltage is equal to total current times total resistance, which would be the formula VT equals ITRT, which means the total voltage equals the total current times the total resistance. Resistance is equal to the sum of the individual resistances. So you take all the resistances and add them together, and that equals your total resistance. Current is equal throughout the circuit, so your total current is going to be the same as each individual current through the circuit. Voltage is equal to the sum of the individual voltages, so that will be voltage total equals voltage 1 plus voltage 2 plus voltage 3. So you're just going to add the voltages together to make the total voltage. And that is all, this is all for a series circuit. In a parallel circuit, the total voltage is determined by multiplying the total current by the total resistance, or by measuring voltage anywhere in the circuit as voltage is equal throughout the circuit. The total current is found by summing the values of the individual current values. The total resistance is a little different in parallel circuits. It is inversely proportional to the sum of the reciprocals of each individual resistance value. So the rules for parallel circuits is the total voltage is equal to the total current times the total resistance. So the formula will be V total equals I total times R total. So that would be your total voltage equals your current total times the resistance total. The total current is equal to the sum of the individual currents. So the current total is just going to be all of your currents added together. And then voltage is equal throughout the circuit. So your voltage total will be the same as each individual voltage. The total resistance is inversely proportional to the sum of the reciprocals of each individual resistance. So to find your excuse me, to find your total resistance, you will take 1 divided by each resistance and then add them together. There are so many different types of electronic devices that we use on a daily basis. Music players, cell phones, video gaming systems, televisions, and these are all referred to as electronic devices. We also use a lot of devices in healthcare. And an understanding of these 7 electronic devices, you must know each one of these before you will be able to understand the X-ray circuit. Battery, capacitor, diode, protective devices like fuses and circuit breakers, resistor or rheostat, switch, and transformer. A battery is a device that produces electrons through a chemical reaction, stores an electrical charge long-term, and provides an electric potential. A capacitor is like a battery in that it stores an electric charge, but it works very differently in that it cannot produce new electrons and stores the charge only temporarily. A diode, or a solid-state rectifier, is a one-way valve device that allows electrons to flow in one direction only. And you can see the symbols next to each one of those that we use when labeling the X-ray circuit. Protective devices, such as fuses and circuit breakers, these act as emergency devices that break or open the circuit if there is a sudden surge of electricity to the circuit or device. So this act of opening the circuit protects the other circuit elements and the device as a whole. A fuse is simply a section of special wire. Usually it's encased in glass, and it quickly melts if the current flow rises excessively, and this will also open the circuit. A circuit breaker acts in the same manner as a fuse. If the current flow rises excessively, the circuit breaker's internal switch is tripped or opened, stopping the flow of electricity. So this will protect your electrical devices. It will protect your house from a fire if there's too much current flowing. So the protective devices help everything that is electronic, in the house or in your car or in any kind of electrical device that you use. A resistor is a device designed to inhibit the flow of electrons. It precisely regulates the flow of electricity through the part of the circuit where it's placed. And then a rheostat is simply just an adjustable or variable form of a resistor. And you can see next to them the symbols that we use in the circuit. A switch is a device that opens a circuit or breaks the pathway. And then the transformer is a device that can increase or decrease voltage by a predetermined amount. And again, there's the symbols that are used to label the switch and transformer when drawing the circuit. Grounding is the process of connecting the electrical device to the earth via a conductor. And this is because we want that protective measure. The earth is essentially an infinite reservoir of electrons. Any charged object can be neutralized if it is grounded. Positively charged objects take on electrons from the earth. Negatively charged objects give up electrons to the earth until they're neutral. Inside of any electrical equipment, the grounding wire connects to metal parts that are not a part of the circuit, such as the housing. If a live wire happens to touch the housing, the current is conducted away by the grounding wire. This short circuit into the ground wire is going to trip the circuit breaker, shutting off the electricity to the circuit and thereby protecting the electrical circuit. With these concepts and components in mind, electromagnetism and electromagnetic induction are going to start to make more sense to you. So electricity and magnetism are two different parts of the same phenomenon known as electromagnetism. Magnetism is defined as the ability of a material to attract iron, cobalt, or nickel. The magnetic properties of cobalt and nickel assume their pure form. The U.S. nickel coin does not exhibit the strong magnetic properties because it only contains 25% nickel. The rest is made up of copper. Iron is relatively abundant and is used extensively in the creation of magnets and magnetic fields. The nature of magnetic materials is where the orbital electrons of their atoms spin in one direction. Such atoms create tiny magnets. These magnets are called magnetic dipoles. And when these dipoles or atomic magnets form groups of similar aligned atoms, they create a magnetic domain. And then we have these domains that exist in the magnetic materials, but they're not coordinated with each other. When these magnetic materials are placed in a strong magnetic field, the domains align with the external field, and then this organizes them and magnetizes the material, creating a magnet. A magnetic field consists of lines of force in space, and these are called flux, and they have three basic characteristics. First, the lines of the flux travel from the South Pole to the North Pole inside the magnet, and from the North Pole to the South Pole outside the magnet, and this creates an elliptical loop. And you can see that in this figure 4-2. It shows the magnetic flux, the magnetic field consisting of the lines of force going around from north to south and from south to north. The second characteristic is the lines of flux in the same direction repel each other, and the lines of flux in the opposite direction attract each other. The third characteristic is the magnetic fields are distorted by magnetic materials and are unaffected by non-magnetic materials. There are three laws of magnetism that may promote an understanding more of electromagnetism. The first law is that every magnet has a north and a south pole. The second law states that like poles repel each other and opposite poles attract each other. The third law states that the force of attraction or repulsion varies directly with the strength of the poles and inversely with the square of the distance between them. The strength of the magnetic field is measured in the SI unit, Tesla, named for the American physicist Nikola Tesla. Magnetic resonance imaging, or MRI, units used for medical imaging are referred by their magnetic field strength and operate with fields from 0.5 to 5 Teslas. 5 Tesla is currently experimental right now, and it's not used in the diagnostic field. Just as materials can be classified as conductors or insulators, they can also be classified by their magnetic properties. There are 4 categories. Non-magnetic materials, for example, glass, wood, plastic, are not attracted to magnetic fields at all. Diamagnetic materials, water, mercury, and gold, are weakly repelled by magnetic fields. Paramagnetic materials, platinum, gadolinium, and aluminum, are weakly attracted to magnetic fields. And ferromagnetic materials, iron, cobalt, and nickel, are strongly attracted to magnetic materials. And this is very important because when we have patients going into MRI, if they have any ferromagnetic materials implanted inside of their body, then that is a contraindication to an MRI exam. Electricity and magnetism together is called electromagnetism, and they are 2 parts of the same basic force. That is, any flow of electrons, whether in space or in a conductor, that is surrounded by a magnetic field. A moving magnetic field can create an electric current. The principle of electromagnetism was first identified by the Danish physicist Hans Ørsted when he discovered that the needle of a compass is deflected when placed near a conductor carrying an electric current. It was later discovered that the magnetic field surrounding the conductor could be intensified by fashioning it into a coil called a solenoid, and intensified further by adding an iron core to the coil called an electromagnet. Shortly after Ørsted's discovery, there was a British scientist by the name of Michael Faraday, and he found that a moving conductor, such as a copper wire, when put through a magnetic field, it induced an electric current in that conductor. This phenomenon is called electromagnetic induction. Fashioning the conductor into a coil and passing it through the magnetic field increases the induced voltage, and this voltage increases with an increasing number of coils. Increasing the strength of the magnetic field, or the speed with which the conductor is passed through, the magnetic field also increases the induced voltage. So with the electromagnetic induction, current may be induced to flow in a conductor by moving that conductor through the magnetic field, or by placing the conductor in a moving magnetic field. There are two forms of electromagnetic induction. They are mutual induction and self-induction, and these are both used in the operation of the X-ray machine. Mutual induction is the induction of electricity in a secondary coil by a magnetic field. The coil on the left is connected on an AC source. A magnetic field is associated with the flow of electricity, and AC switches the direction of flow in the cycle. Each time AC switches direction, the associated magnetic field also changes. So the north and the south poles of the magnetic field are directionally oriented to the current flow, and when the current changes the direction, the previous magnetic field dies away and a new one is created that is opposite in orientation and oriented to the new current flow direction. The important part of this phenomenon is that a moving magnetic field is now created. So the previous field collapses and a new one expands, then the current changes direction again and the process starts all over. When this moving magnetic field is placed near a secondary coil, the coil shown here to the right on the picture, electricity is induced to flow in that coil. This is also AC because it too switches with the changing magnetic fields. So they both have alternating current. So coil A is the primary coil and it's connected to AC power. And then coil B is the secondary coil, and as the fluctuating magnetic field from A moves back and forth through the turns of B, a secondary current is induced. Self-induction is a bit more complex, requiring an understanding of Lenz's law, which states that an induced current flows in a direction that opposes the action that induced it. So in this case, the action is the changing magnetic field. So going back to the example of the primary coil that we saw back on the other slide, the magnetic field is created in this coil and expands outward from the center of the coil. As it does so, it cuts through the turns of the coil, and this act of cutting creates a current within the same conductor that opposes the original one, and this is the Lenz's law. Using DC, which is the direct current, this phenomenon is short-lived because the magnetic field reaches the maximum strength and the cutting action stops. But with alternating current, this process repeats with each change of direction. The result is a fluctuating magnetic field cutting back and forth through the single coil, and it's going to induce a constant secondary current that opposes the original. And this process is called self-induction, and it's used in the X-ray circuit in the auto transformer design, which we'll get to in a minute. So this figure here shows a generator, and it shows as the loop is rotated in the magnetic field, a current is induced in that loop. And you can see the hand right there is rotating that loop. Electromagnetism and electromagnetic induction have many applications in electric equipment and the electrical circuit. They have particular interest in understanding the X-ray circuit as far as the electric generators, the electric motors, and the transformers. Electric generators are devices that convert some form of mechanical energy into electrical energy. And examples of that are the force of water through a dam, steam, which is created by burning some type of fuel, turning a turbine, or the wind turning a windmill turbine. In its simplest form, rotating a loop of wire in a magnetic field induces a current in that loop through electromagnetic induction. Remember, when the loop cuts the magnetic flux lines, a current is induced. So the more complex design uses coils of wire forming an armature, and that is rotated in a magnetic field by some mechanical means. Right here, you can see that it's, being created and rotated by man. So the mechanical input is actually the hand, and it's actually rotating that loop inside the magnet. And then the light bulb is that electrical circuit or electrical means that is created. Electric motors are devices that convert electrical energy to mechanical energy through electromagnetic induction. In a simple motor, we have an armature that is placed in an external magnetic field, and the armature is supplied with AC. As discussed previously, every flow of current has an associated magnetic field. So the magnetic field associated with the armature is oriented such that the North Pole is next to the North Pole of the external field, and the South Pole is next to the external South Pole. Because like poles repel, the armature flips to its orient. It orients itself to the external field, and then at the same instant, the two magnetic fields align, and the AC current changes direction. Then we have a new magnetic field that's created in the armature, which again is not aligned to the external field, and the armature rotates again. This process is continuous, converting electrical energy to mechanical energy. And we'll talk about that when we talk about the induction motor later on. But transformers are the devices used to increase or decrease voltage or current through electromagnetic induction. Transformers are named for their effect on voltage. A step-up transformer is one that increases voltage. A step-down transformer decreases voltage. And you should know that the change in voltage and current is an inverse relationship. So as voltage is increased, current decreases. And as voltage is decreased, current increases. The relationship is expressed using the transformer law for voltage and current, where V equals voltage, I equals current, N equals the number of turns in the coil. S equals the secondary coil, and P is the primary coil. The transformer law for voltage is Vs divided by Vp equals Ns divided by Np. So that is voltage, secondary coil, the voltage of the divided by the voltage of the primary coil equals the secondary coil number of turns divided by the primary coil number of turns. And this is a direct relationship. So if a transformer has 10 turns in the primary, 50 turns in the secondary, and 110 volt is applied, what is the output voltage? So you would take voltage of the secondary coil divided by 110, which is that voltage, the first voltage, equals 50 divided by 10. And then you would take the voltage of the secondary equals 5 times 110. And then multiply that. And so your secondary coil voltage would be 550. The transformer law for current is IS divided by IP equals NP divided by NS. And this is an inverse relationship. So for an example, if a transformer has 10 turns in the primary, 50 turns in the secondary, and 5 amps is applied, what is the output current? So we're trying to find the new current. So you would do IS divided by 5. That's going to equal 10 divided by 50. IS is going to equal 5 times 0.2. And then IS equals 1. So your new output current is 1. The relation of voltage to current in a transformer is IS divided by IP equals VP divided by VS. This is also an inverse relationship. And for an example, if a transformer has an input voltage of 110, an input current of 5 amps, and an output voltage of 550, what is the output current? So we've got IS divided by 5 equals 110 divided by 550. IS equals 110 divided by 550 times 5. IS equals 1. So you're just cross multiplying there. When alternating current is flowing through the primary coil, it has an associated fluctuating magnetic field, and this collapsing and expanding magnetic field induces the electricity in the secondary coil. So you have a primary coil and a secondary coil in each type of transformer. You can see to the left, it's the closed core transformer, and it's an iron core with a primary coil and a secondary coil, but it just has one opening. And then the shell type transformer will have 2 openings, the iron core with the primary coil and the secondary coil, and that is the shell type transformer. The difference in the voltage induced in the secondary coil is going to depend on the ratio of the number of turns of wire in the 2 coils. For example, if there are twice as many turns in the secondary coil as in the primary, the voltage in the secondary coil is twice that of the primary coil. So if there are half as many turns in the secondary coil, the voltage is half that in the primary coil. More sophisticated designs of the transformers are used in the X-ray equipment that we use, such as a closed core and a shell type transformer. And these incorporate a ferromagnetic core to maximize the efficiency. In this figure here, you can see the 2 types of transformers, the basic design of a closed core and then the shell type transformer. The iron cores of each of these are going to increase the magnetic field strength and the transformer efficiency. One final type of transformer important to the X-ray machine is the auto transformer. This transformer is going to operate on the principle of self-induction, and this transformer only has one coil of wire around a central magnetic core, not to be confused with the shell type that we saw earlier, which has the two coils of wire. The auto transformer is used as both the primary and secondary coil. The outside wires are attached at different points along the coil, and the induced voltage is going to vary depending on where the connections are made. This figure here shows the auto transformers highlighted in orange, and it also shows the orientation of the auto transformer in the big X-ray circuit. Shown on this slide here is a general drawing of the X-ray circuit. The X-ray circuit may be divided into three sections. We have the primary circuit, the secondary circuit, and then the filament circuit. And each section has specific components and very important roles that they play with the X-ray machine. The primary circuit is indicated in orange, the secondary circuit in blue, and the filament circuit in purple. And this is the basic X-ray circuit. The primary circuit consists of the main power switch, which is connected to the incoming power supply, the circuit breakers, the auto transformer, the timer circuit, and the primary side of the step-up transformer. The secondary circuit consists of the secondary side of the step-up transformer, the milliampere meter, a rectifier bank, and the X-ray tube, except for the filaments. The filament circuit consists of a rheostat, a step-down transformer, and the filaments. Shown here is a labeled version of the basic X-ray circuit, and we will go over every component of this X-ray circuit in the following slides. Beginning in the primary circuit, we have the main power switch, and this is simply an on and off switch for the power unit and is connected to the power supply of the facility where the X-ray machine is stationed. Because the incoming power is not consistent 220 volts, we have to have a line compensator. This device is usually wired to the auto transformer, and it automatically adjusts the power supply to the X-ray machine to precisely 220 volts needed. The circuit breakers are included in the primary circuit to protect against short circuits and electric shock. Then we have the auto transformer. It's an adjustable transformer controlled by the KVP selector on the operating console. When the radiographer selects the KVP setting, we will control this transformer. This transformer operates on the principle of self-induction. So when we select a KVP setting, we will determine the number of turns on the secondary side to be included in the circuit element, and with it, the output voltage. Because of its function, the auto transformer is sometimes called the KVP selector, and its primary purpose is to provide a voltage that will be increased by the step-up transformer to produce the KVP selected at the operating console by us. The step-up transformer is used to increase the voltage from the auto transformer to the kilovoltage that's necessary for X-ray production. So this transformer is the dividing line between the primary and secondary circuits. The primary coil is in the primary circuit and the secondary coil in the secondary circuit. Unlike the auto transformer, the step-up transformer is not adjustable, and it increases the voltage from the auto transformer by a fixed amount. The timer circuit, or exposure timer, is located in this section because it is easier to control, turn on and off, a low voltage than a very high one. There are several variations of the exposure timer. The first variation is a synchronous timer. This is based on a synchronous motor. The motor is designed to turn a shaft at precisely 60 revolutions per second, and this shaft turns a disc, which is connected to on and off switches, through reduction gears. The exposure time selected determines the reduction gear used, and therefore the time it takes the disc to move from the on switch to the off switch. And then there is a second variation of a exposure timer or timer circuit, and this is the electronic timer. It is a very sophisticated and accurate timer, and this is the most widely used one today. This timer is based on the time it takes to charge a capacitor through a variable resistor. Once the capacitor receives its pre-programmed charge, it terminates the exposure. The time it takes to charge this capacitor to its pre-programmed level is controlled by the variable resistor. To achieve a 1-second exposure, the resistance is increased so that it takes longer to charge the capacitor. This includes the inherent electrical delays, which is a total time of 1 second. To achieve a 1 millisecond exposure, there is virtually no resistance, and the capacitor charges very quickly, and the timer terminates the exposure. This is one application for a resistor in the X-ray circuit. The mass timer is a variation of the electronic timer, but it monitors the current passing through the X-ray tube and terminates the exposure when the desired mass is reached. Because of the way it functions, this timer is located in the secondary circuit instead of the primary circuit. Basically, just like the timer, we have the AEC device, which is the automatic exposure control. This device operates a little bit differently from others in that it uses the patient's body part of interest as the variable in determining when to terminate the exposure. The AEC uses a device called an ionization chamber. This is a radiolucent device that is placed between the patient and the IR. When X-rays interact with this chamber, its atoms are ionized, which means the electrons are removed, and this creates an electric charge. This charge becomes a signal that terminates the exposure. The AEC can be adjusted or calibrated so that more or less of a charge is needed before the signal to terminate the exposure is sent. The AEC calibration is performed by the installation personnel, so we have nothing to do with that. The installation personnel do that. They do this by exposing phantoms until the desired density or the image quality factor is achieved. This amount of exposure varies with the IR, and the AEC must be recalibrated if we have a receptor change. For example, going from film screen speed to another, or from film screen to a cassette-based digital system. Once the AEC is calibrated, the patient becomes the variable. As X-rays exit the patient on the way to the IR, they pass through the ionization chamber, causing ionization. Once the pre-programmed magnitude of electric charge is reached, the exposure is terminated. The length of the exposure is determined by the thickness and the density of the area of the patient that is placed over the ionization chamber. For an example, if we have an infant and we're doing an abdomen, and then we have an adult and we're doing an abdomen on them as well, they could be placed over the ionization chamber, and although both are abdomens, the exposure time is going to be very different because of the differences in the tissue thickness of the infant to the adult. So it takes longer for enough X-rays to exit the larger abdomen, which would be the adult abdomen, than it does the infant abdomen to create the signal in the chamber. To this point, the radiographer has selected the exposure factors, KVP and mass, among other parameters, and pressed the exposure button. In the primary circuit, this results in a voltage being determined by the autotransformer, and applied to the primary side of the step-up transformer. A voltage is also selected from the auto transformer and applied to the filament circuit. With the voltage and current selected and traveling, the stage is set for the rest of the circuit. So now we go on to the secondary circuit. The secondary circuit begins with the rest of the step-up transformer. The milliampere meter, or MA meter, is simply a device placed in the secondary circuit that monitors the X-ray tube current. In a general X-ray circuit, AC is necessary for transformers to operate correctly, which means they are providing the moving magnetic field. To allow the X-ray tube to be exposed to AC would be disastrous. So we need direct current. Within the X-ray tube, the current must always flow from anode to cathode and electrons from cathode to anode. So we cannot have alternating current. We have to have direct current going from anode to cathode at all times. So to achieve this, we have rectifiers that are used. The rectifier commonly used in today's X-ray circuit is a solid-state rectifier. This device is made up of two semiconducting crystals. One is a p-type crystal, and the other is an n-type crystal. So the solid-state rectifier is also called a p-n junction. The p-type crystal has an abundance of electron traps, whereas the n-type has an abundance of freely moving electrons. These two crystals are joined to form the solid-state diode. When a positive charge is placed on the p-type crystal and a negative is placed on the n-type crystal, the solid-state diode will conduct electricity. Both the traps from the p-type crystal and the electrons from the n-type crystal move toward and across the p-n junction. And this will allow the current to flow through. When the AC cycle reverses and the p-type crystal receives the negative charge, and then the n-type crystal receives the positive charge, the solid-state diode will not conduct. This is because the traps and electrons basically stay at home. They do not move to the junction, and then there is no current conducted. In this image here, you can see the solid-state rectifier. It's showing its conduction and its non-conduction phase. So the one to the left is the conduction, and the one to the right is the non-conduction. And you can see the change in the polarity in each half of the image, where it goes from positive to negative and then negative to positive. To be used more effectively, rectifiers are arranged in pairs, and this is so that the AC cycle has an open path from each direction. It is possible to use only two rectifiers, but then this suppresses or basically wastes the negative half of the cycle, and then simply serves to protect the X-ray tube during that phase. One half of the AC cycle flows through the X-ray tube, and the other half, which would otherwise flow through the X-ray tube the wrong way, is blocked. This type of waveform is called a half-wave rectification. The figure here shows AC on the top. It shows alternating current, and on the bottom it shows the half-wave rectification. This image here is a 4-rectifier bank. You can see the color coding of the pair that operates together in each half of the cycle. When 4 rectifiers are used, full wave rectification is achieved. You can see the arrangement of the 4 rectifiers in this figure here, and they are highlighted to show which 2 are in use with each half of the cycle. With 4 rectifiers arranged in this way, both halves of the AC cycle are used. The resulting waveform is illustrated in the top of this figure, and you can see it's single phase full wave. You can see that it is inverted in the negative half of the cycle, thereby making use of the entire cycle. You can also see that the energy fluctuates from 0 on the line to the maximum voltage or peak of the wave, and this is called the ripple. And in this case of a single phase full wave, it is 100% ripple. Although single phase is full wave power is much more desirable and certainly less wasteful, this 100% ripple is a problem because the X-rays vary in energy from the kVp that is selected on the operating console, which is the maximum energy available, and it goes all the way to 0. One solution is to use 3 AC waveforms at the same time. With a bit of engineering, you can use these 3 waveforms that can be phased or synchronized. Each is generated independently and then phased so that each one is 120 degrees out of step with the next, or out of step by 1/3. The result is a waveform like the one shown in the middle figure, and this is the alternating currents. It's a terrible waste not to rectify the waveform. When we rectify each one as if they were a single phase waveform, the X-ray tube sees the waveform like the one in the bottom figure, which is the 3-phase full wave rectification. This is referred to as 3-phase power. Although this is obviously less ripple than the single phase waveform, it still has ripple. Depending on the number of rectifiers and engineering, it will have anywhere from 13% ripple, which is 3-phase 6-pulse, to 3.5% ripple, which is 3-phase 12-pulse. And this translates into X-rays being produced anywhere from 87% to 100% of the kVp selected on the console for 3-phase 6-pulse, and then 96.5% to 100% for 3-phase 12-pulse. The next step in the quest to improve the waveform is the use of a high-frequency generator in place of the standard 60 Hz generators. The standard 60 Hz incoming power is first fully rectified, and then it's sent through a capacitor bank where it is smoothed out, and then from there it passes through an inverter circuit that chops this DC waveform and converts it to the high-frequency alternating current. This low-voltage, high-frequency AC is then passed through a step-up transformer, and it converts it to a high-voltage AC that we use for the X-ray tube. It is again passed through rectifiers where it is again fully rectified, and finally through high-voltage capacitors where it is smoothed to provide the X-ray tube with a near constant potential voltage waveform. These generators reduce the ripple that are seen by the X-ray tube to less than 1%. You can see in this figure here, it's going to demonstrate the resulting waveform. It's a high-frequency full wave rectification. These generators are smaller, they're lighter, they cost less, and they offer better exposure reproducibility. But you want to keep in mind that through all of this, the rectifiers are the one-way valves, and they're necessary to route the electricity through the X-ray tube correctly. The X-ray tube, with the exception of the filaments, is a part of this section. And because the X-ray tube head assembly is the subject in Chapter 5, we won't really talk about that until we get to that chapter. Within the secondary circuit, the pressing of the exposure button has sent a voltage through the step-up transformer, increasing it to the kilovoltage selected and indicated on the control console by the RT. This kilovoltage is passed through a series of rectifiers so that it travels through the X-ray tube correctly to produce our X-rays. A large positive charge now resides within the anode and a large negative charge with the cathode that is within the X-ray tube. All that's lacking is the source of electrons on which the kinetic energy will ride, which brings us to the filament circuit. Now in the purple highlighted here, this is the filament circuit, and these are all the components of the filament circuit that we will talk about in the next slide. The filament circuit begins with the rheostat. The rheostat is a variable resistor controlled by the MA selector on the operating console. The MA parameter is called tube current because it reflects the rate of flow of electrons passing through the X-ray tube during the exposure. When the RT adjusts the milliamperage on the operating console, he or she is adjusting this rheostat and the amount of resistance in the filament circuit. And then the amount of current applied to the filament, which is called the filament current, is also set in the X-ray tube. The higher the MA station number, the lower the resistance. So a 1000 MA station will have very little resistance to the flow of electricity, whereas if you set a 100 MA station, it will have considerable resistance. The goal of this circuit, the filament circuit, is to literally boil off the electrons out of the filament wire. Normally, a rather large filament current of about 5 to 7 amperes is required to produce a tube current in the range of MA. The thermionically emitted electrons are needed for X-ray production and represent one more step in the manipulation of electricity. In the filament circuit, we are boiling these electrons off of a very small wire, and we have to precisely control the current that is applied. If the current is too high, this tiny wire will be damaged or destroyed. So you should note that the exposure timer works in concert with the rheostat. The rheostat controls filament temperature and the rate at which electrons are boiled off the filament. The timer determines the duration of the process, and together they determine the quantity of electrons boiled off of the filament and available for X-ray production. A step-down transformer is used also in the filament circuit to increase the current by reducing the voltage that is applied to the filament, hence the word step down. The purpose of this filament circuit is to control the degree and duration that the filament is heated, and this will control the number of electrons that are boiled off and ultimately become the tube current. Although the step-down transformer does reduce the voltage that is applied to the filament, we are concerned with the current through the filament. So we generally talk about the output current of this transformer rather than the voltage. Remember that as voltage decreases, current increases, and they are inversely proportional. The final piece of the filament circuit are the actual filaments. A general purpose radiographic tube typically has 2 filaments, and these are tiny little coils of wire housed in the cathode of the X-ray tube. The design and purpose of the filaments will be covered later on in the chapter, but they are represented on the operating console by a large focal spot and a small focal spot. So when we are selecting one of these, we're literally selecting the filament to be heated and used for that exposure. And you can see here in this picture, this is a filament with small wire coils, and it is within the cathode focusing cup. Within the filament circuit, when the exposure button is pressed, a voltage and a current is sent through the filament circuit. The quantity is controlled by a rheostat to reflect the MA selected and indicated on the control panel. A step-down transformer is used to reduce this voltage and increase current. So remember that inverse relationship again. As voltage decreases, current increases. The current heats the filament chosen by the RT and begins boiling off the electrons. The time selected by the RT controls the duration that the voltage and current in the X-ray tube is applied. So now we are going to walk through the X-ray circuit's operation from the incoming power to the X-ray tube. So the appropriate place to begin is the actual operating console. So this is the first place that the RT is going to be setting their technical factors. So like the controls of an automobile, there are options and arrangements, but all have the basic options in common. The operating console offers options for selecting KVP, MA, exposure time, and focal spot size. If the unit is equipped with an AEC, or anatomic programming, those options are also displayed. The same is true for bucky selection, if both a table and a wall bucky are available. The process begins when the radiographer selects an exposure technique, which specifies the KVP, the MA, the exposure time, and the focal spot. From here, it is the easiest to follow the sequencing of events in two parts. First, we follow the voltage through the primary and secondary circuits. Then we follow the current through the filament circuit. The KVP selected adjusts the auto transformer and determines the number of turns on the secondary side necessary to produce the voltage through self-induction, and then this will be sent to the step-up transformer. The step-up transformer increases the voltage by a fixed amount and through mutual induction produces the KV selected on the operating console. This transformer represents the transition from the primary circuit to the secondary circuit. Once the KV is created, it must be rectified for the X-ray tube. Where the X-ray tube is concerned, the electrons must always flow from cathode to anode. Cathode is negative and the anode is positive, so it goes from negative to positive. The solid-state rectifiers are also used, and they route the electricity through the X-ray tube. The number of rectifiers used depends on the circuit type. Remember, the rectifiers are the one-way valves, and they route the current from positive to negative and electrons from negative to positive. After passing through the rectifiers, the electricity creates a large positive charge on the anode of the X-ray tube and then a large negative charge on the cathode or the focusing cup, which is the part of the tube that surrounds the filaments. So at this point, we return to the auto transformer to discuss the other half of the process. The filament circuit draws electricity from the auto transformer, which then travels to the rheostat. The rheostat is a variable resistor controlled by the MA selector on the actual operating console itself. And then the focal spot selector represents the two filaments, the one large and the one small focal spot. When the MA station is selected, the appropriate filament was also selected. So we would select small for small MA stations and large for large MA stations. The selected MA station sets the resistance in the filament circuit by the MA selector on the operating console, and it's tied into the focal spots, the small and large focal spots. From the rheostat, electricity then travels to the step-down transformer. Remember, we are more concerned with the current output in this case than with the voltage. And as voltage decreases, current increases. So it is inversely proportional relationship. The adjusted current from the step-down transformer then travels directly to the filament located within the focusing cup of the X-ray tube. And then this current heats the filament to the point at which electrons are literally boiling off. It's way too hot for these electrons, so they're boiling off and they're going from the cathode, which is the filament side, over to the anode. So now we can join the two halves of the process. A group or cloud of electrons is created by the filament circuit by heating the filament, and that's called the electron cloud. The kilovoltage applied to the X-ray tube creates a large positive charge on the anode and a large negative charge on the cathode where the focusing cup is. The large positive charge attracts the electrons boiled off of the filament, giving them tremendous kinetic energy in the process. Remember, opposites attract. And in the short 1 to 3 centimeter gap between the cathode and anode, the electrons from the filament reach speeds of about 1/2 the speed of light. The large negative charge on the cathode keeps the electrons crowded together. Otherwise, they would repel each other and scatter throughout the tube. The electrons travel across to the anode and interact there to produce X-rays until the timer circuit terminates the process.